It is the most familiar object in our sky, a constant presence that has governed the rhythm of life for as long as life has existed. Its light has been the first thing seen by every human who has ever lived. Its warmth, the first sensation felt. Yet, for all its familiarity, it remains a place of profound mystery and awesome power. Unraveling its secrets is one of the greatest adventures in the history of human inquiry. A story we are about to tell. We love bringing these epic narratives of science to life, so be sure to subscribe to the channel to be notified of all our future stories. The journey to understand our star is a tale that spans millennia. From the first philosophers who dared to question its divine nature to the robotic probes now touching its fiery atmosphere. It is a story of cosmic scale, of nuclear fire, and of our own origins, written in the very light that reaches us across the silent void of space. To truly understand this star is to understand the heart of our own world, the source of its energy, and the anchor of its existence. It is the necessary first step in knowing our true place in the universe. To truly comprehend our place in the cosmos, we must begin with the star that anchors our existence, the celestial furnace that holds our world in its unwavering embrace. We call it the sun, but its scale and power are of an order so immense that language itself struggles to convey the reality. It is not merely the center of our solar system. It is, for all practical purposes, the solar system itself. Imagine gathering every planet, every moon, every asteroid, comet, and speck of dust that orbits this star, from the scorched plains of Mercury to the icy wanderers in the Oort cloud. If you could place all of this material onto a cosmic scale, you would find that the sun alone accounts for an astonishing 99.86% of the total mass. Everything we know, Earth included, is part of the remaining fraction, the cosmic dust bunnies left over from the formation of this one colossal object. This overwhelming dominance is not just a statistic, it is the fundamental law of our celestial neighborhood. The sun's mass, a staggering 333,000 times that of our own Earth, generates a gravitational pull so profound that it dictates the motion of everything around it, choreographing the silent, orbital dance of worlds. It is the reason Earth follows its yearly path, the reason Jupiter commands its own miniature system of moons, and the reason comets journey from the dark frontiers only to swing back around this central pivot. This gravitational authority is absolute, but to speak of its mass is still an abstraction. To truly feel its scale, we must try to envision its physical volume. It is a classic thought experiment, but a powerful one. If you could somehow hollow out the sun and begin filling it with planets the size of our own, you would find that there is room for approximately 1.3 million Earths. This is a volume so vast that it transcends our terrestrial experience. And its exterior is no less humbling. The surface area of the sun, the visible, seething layer we call the photosphere, is 11,990 times greater than the entire surface area of our world, oceans and continents combined. Yet for all this colossal size and power, the sun possesses a remarkable, almost impossible elegance. One might expect such a gigantic, turbulent body of plasma to be a chaotic, bulging mass. Instead, it is almost a perfect sphere. The force of its own immense gravity pulls all of its substance inward with incredible uniformity, while its rotation is slow enough to prevent any significant distortion at its equator. The result is a celestial orb of breathtaking geometric precision. If you were to measure its diameter from pole to pole and compare it to its diameter across the equator, you would find a difference of a mere 10 kilometers, roughly 6 miles. Across a body whose total width is nearly 1.5 million kilometers, this variation is practically negligible, making the sun one of the most perfectly spherical natural objects ever observed by humanity. This perfect sphere is not adrift in an empty void, but is on an epic journey of its own. Zooming out from our local planetary system, we find ourselves in a vast, spinning island of stars we call the Milky Way galaxy. Our sun is but one of hundreds of billions of stars in this city of light, and it resides in a relatively quiet suburban spiral arm. From the thrumming, supermassive black hole at the galactic center, our sun is located a great distance away, estimated to be between 24,000 and 26,000 light years. A light year, the distance light travels in a single year, is a measure of such profound scale that it forces us to reconsider our place in the universe. Our entire solar system is hurtling through the galaxy on an immense orbit, forever bound to the collective gravity of the Milky Way. Yet, for all this cosmic wandering, the sun's relationship with Earth is one of remarkable constancy. We live in its immediate presence, bathed in the light and heat that make our world habitable. The average distance that separates us from our star is approximately 150 million kilometers, or 93 million miles. This specific distance is so fundamental to our understanding of the cosmos that astronomers have designated it as a unit of measurement in its own right, the astronomical unit. It is our cosmic yardstick, the standard by which we measure the orbits of other planets and the scale of our solar system. This distance allows for the delicate balance of energy that permits liquid water to flow and life to flourish. Up close, the dimensions of our star reaffirm its grandeur. The sun is so large that its diameter is about 109 times the width of the Earth. Its circumference at the equator is a staggering 4,379,000 kilometers. And from its core to its visible surface, its radius measures 695,700 kilometers, which is about 432,228 miles. This is the physical entity that commands our skies, a sphere of incandescent plasma whose sheer size and mass forge the very environment of our home world. Having grasped its titanic scale, we must now venture into the very substance of the sun, to understand not just its size, but its soul. If we could take a sample of our star, we would find it is forged from the simplest and most abundant materials in the universe. By mass, it is composed of about 73% hydrogen and 25% helium. These two elements are the primordial building blocks of the cosmos, the raw material created in the first few minutes after the Big Bang. The sun is, in essence, a vast, consolidated cloud of this primordial gas, its existence a direct link to the dawn of time itself. The remaining 2% of its mass is a subtle but crucial cocktail of other elements. In the lexicon of astronomy, any element heavier than hydrogen or helium is referred to as a metal, a convention that can seem strange to a geologist or chemist. This means that elements we think of as gases, like oxygen and carbon and neon, are considered metals in stellar terms, alongside more familiar ones, like iron. These heavier elements were not created in the Big Bang, but were forged in the hearts of earlier generations of massive stars. These ancient stars lived out their lives and died in cataclysmic supernova explosions, scattering their newly created elements across the galaxy like cosmic seeds. Our sun, and indeed our entire solar system, formed from a nebula enriched by this stellar stardust, making us the descendants of long-dead stars. This elemental composition exists in a state that is entirely alien to our everyday experience. This brings us to a fundamental truth about our star. It has no solid surface to stand on. It is not a world of rock or metal, but an incandescent sphere of plasma, the fourth and most energetic state of matter. At the extreme temperatures found in the sun, atoms are subjected to such violent collisions that their electrons are stripped away from the nuclei, creating a superheated, electrically charged soup of particles. This plasma is not uniform. It is structured in a series of concentric shells, each with its own distinct character, beginning with the furnace at its very heart. This is the core, a region of unimaginable pressure and heat, where the temperature climbs to an astonishing 15 million degrees Celsius, which is a staggering 27 million degrees Fahrenheit. Here, in this cosmic crucible, the sun's energy is born through the process of nuclear fusion. Outside the core lies the vast radiative zone, a region so densely packed with plasma that energy struggles to escape. The photons of light generated in the core begin a long and arduous journey, being absorbed and re-emitted by particles countless times, ricocheting in a random walk that can take over 170,000 years to complete. Beyond this is the convection zone, where the character of energy transport changes dramatically. Here, the plasma behaves much like a boiling pot of water, with immense, churning currents. Hot columns of plasma rise toward the surface, release their heat, and then sink back down to be reheated, creating a perpetual, roiling motion. It is this convective layer that brings the sun's energy to its surface, the boundary between its interior and its atmosphere. And it is this atmosphere where the sun truly reveals its complex and dynamic personality, itself divided into 3 distinct layers. The first and innermost of these atmospheric layers is the photosphere. This is the visible surface of the sun, the layer from which most of the light and heat we receive finally escapes into space. Though it appears solid from our vantage point on Earth, it is a turbulent layer of plasma several hundred kilometers, or a few hundred miles, thick. Just above this lies the chromosphere, a far more tenuous and irregular layer, named from the Greek word chroma for color. It often appears as a fleeting reddish-pink rim during the opening and closing moments of a total solar eclipse. It is a region of immense magnetic complexity, a forest of fiery jets and arching loops of plasma. But it is the outermost layer of the atmosphere that presents one of the greatest mysteries in all of solar physics. This is the corona, a ghostly, ethereal halo of plasma that stretches millions of kilometers, or millions of miles, into the blackness of space. For centuries, it was visible to humanity only during the brief, haunting moments of a total solar eclipse, a pearly white crown surrounding the black disk of the moon. Here, in this tenuous and beautiful halo, the established laws of thermodynamics appear to be turned on their head. While the visible surface of the photosphere simmers at a few thousand degrees, the temperature in the corona inexplicably soars to an incredible 2 million degrees Celsius, which is about 3.5 million degrees Fahrenheit. How this outermost, least dense layer of the atmosphere can be hundreds of times hotter than the fiery surface just below it is a profound and as yet unsolved puzzle known as the coronal heating problem, a mystery that continues to drive solar science to this day. Bridging the gap between the sun's lower atmosphere and its ethereal, superheated crown is a region of utter physical bewilderment known as the transition region. This is not so much a place as it is a razor-thin, invisible boundary, a zone of sheer thermal violence where the laws of nature seem to take a bizarre turn. In the space of just a few hundred kilometers, or a few hundred miles, the temperature of the solar plasma doesn't just climb, it erupts, soaring from the relatively modest tens of thousands of degrees in the chromosphere to over 1 million degrees in the corona. It is a mystery that has puzzled scientists for generations, a thermal cliff so steep that it defies simple explanation. Understanding this impossibly sharp temperature gradient is the very key to solving the coronal heating problem, but it remains one of the most stubborn enigmas in heliophysics. Moving our attention downward to the visible photosphere, we witness the direct consequences of the immense forces churning within the sun. Here, the otherwise brilliant, uniform face of the star is often marred by dark blemishes, temporary islands of relative cool known as sunspots. These features, which can be larger than the Earth itself, are not truly dark. They are still blazing at temperatures of several thousand degrees. They only appear as dark patches because they are cooler and therefore less bright than the incandescent plasma that surrounds them. For centuries, their nature was a complete mystery. When early astronomers like Galileo Galilei pointed their newly invented telescopes at the sun, the sight of these imperfections shattered the ancient philosophical ideal of a perfect, unchanging heavens. We now understand that sunspots are the tangible manifestations of intense, localized magnetic fields. These fields are so powerful that they punch through the photosphere from the interior, inhibiting the normal flow of heat from the convection zone below, and thus creating the cooler, darker regions we observe. Where there are sunspots, there is magnetic instability. And this instability often leads to some of the most spectacular and violent events in the entire solar system. At times, the complex, tangled magnetic field lines above a sunspot group can suddenly snap and reconfigure themselves into a simpler, more stable arrangement. This event, known as magnetic reconnection, unleashes a colossal amount of stored energy in a blinding flash, giving birth to a solar flare. A flare is a sudden, cataclysmic detonation on the sun's surface, a burst of radiation and high-energy particles that can release the energy equivalent of millions of 100 megaton hydrogen bombs in a matter of minutes. These are not gentle eruptions. They are the most powerful explosions in our solar system. Yet, the sun's magnetic field also expresses itself in forms of breathtaking beauty and grace. Anchored in the photosphere, often near sunspot regions, are enormous, arching structures of plasma called solar prominences. Unlike the explosive, instantaneous violence of a flare, a prominence is a far more subtle and long-lived feature, a glowing tendril of solar material that is suspended and shaped by the powerful magnetic field lines that loop high into the corona. These colossal arches, which can stretch for hundreds of thousands of kilometers or hundreds of thousands of miles across the solar limb, can persist for days or even weeks. A silent, slow motion. Ballet of incandescent gas tethered by invisible magnetic forces. To place all of this remarkable activity in context, we must classify our star among its cosmic peers. The Sun is formally known as a G-type main sequence star, a designation that is rich with meaning. The main sequence part of its name tells us that it is in the long, stable, hydrogen-burning phase of its life, its adulthood. The G-type classification refers to its surface temperature and its color. It is also often called a yellow dwarf, though this familiar nickname is a slight misnomer. While it is a dwarf star compared to celestial giants like Betelgeuse or UY Scuti, it is actually larger and brighter than the vast majority of stars in the Milky Way, most of which are small, dim red dwarfs. The dedicated scientific discipline that seeks to unravel all of these interconnected phenomena, from the nuclear furnace in the core to the star's influence on the planets, is known as heliophysics. It is a holistic field that combines elements of astrophysics, plasma physics, and planetary science in a unified quest to understand our star's complete sphere of influence. And that sphere of influence extends far beyond its light and gravity. The Sun generates a stupendous magnetic field that permeates the entire solar system, creating a vast, protective bubble called the heliosphere. This is the Sun's magnetosphere, an immense cocoon of charged particles and magnetic fields that shields all the planets, including Earth, from the harsh radiation of interstellar space. The Voyager spacecraft, launched in the 1970s, traveled for nearly 40 years before they finally crossed the outer boundary of this bubble, the heliopause, and entered the space between the stars. The engine that drives all of this magnetic activity, the sunspots, the flares, the prominences, and the heliosphere itself, is the Sun's peculiar rotation. Our star does not spin as a solid body. It is a fluid sphere of plasma that rotates on its axis, but it does so at different rates depending on latitude. This phenomenon, known as differential rotation, is the key to its dynamism. At its equator, the Sun completes a full rotation in about 25 Earth days. Near its poles, however, the rotation is significantly slower, taking around 35 days to complete a single turn. This shearing, twisting motion churns the Sun's plasma and relentlessly tangles its magnetic field lines, stretching and concentrating them like twisted rubber bands. It is this process that generates the intense magnetic fields that create sunspots and ultimately powers the star's explosive activity. And all the while, this rotating, active star is on a far grander journey, one that dwarfs the orbits of its planets. The Sun, along with its entire system of worlds, is in a constant, stately orbit around the center of the Milky Way galaxy, a single cosmic year that takes an almost unimaginable 225 to 250 million Earth years to complete. As our Sun embarks on its immense quarter-billion-year odyssey around the heart of the Milky Way, it does so at a speed that is difficult to truly internalize. Our entire solar system, a gravitationally bound family of planets, moons, and asteroids, is hurtling through the interstellar medium at a blistering 220 kilometers per second, which is approximately 137 miles per second. This is not a gentle drift. It is a relentless, high-speed journey through the galactic suburbs. At this velocity, we cover a distance equivalent to the circumference of the Earth in just over 3 minutes. Yet the galaxy is so incomprehensibly vast that even at this breakneck pace, the completion of a single orbit takes longer than the dinosaurs walked the Earth. Our cosmic address is not a fixed point, but a vessel on an eternal voyage. We reside within one of the Milky Way's great spiral arms, a flowing river of stars, gas, and dust known as the Orion Spur, a minor but beautiful structure nestled between the larger Sagittarius and Perseus arms. Here, in this relatively tranquil region of the galaxy, our sun was born some 4.6 billion years ago, and it is here that it will spend the majority of its long and stable life. The source of this stability, the engine that powers the sun's light and heat and will continue to do so for billions of years to come, lies deep within its core. It is a process that is both elegant in its simplicity and terrifying in its power: nuclear fusion. In the crushing pressures and searing temperatures of the solar core, the most fundamental of all elements, hydrogen, is subjected to forces so extreme that its atomic nuclei are stripped of their electrons and slammed together. Through a series of steps known as the proton-proton chain reaction, 4 individual hydrogen nuclei, which are just single protons, are fused together to create one single nucleus of helium. However, the mass of the resulting helium nucleus is slightly less than the combined mass of the 4 original protons. This tiny, missing fraction of mass does not simply vanish. It is converted into a pure, incandescent burst of energy, as described by Albert Einstein's famous equation E equals mc squared. Every second, the sun converts roughly 600 million tons of hydrogen into helium, and in doing so, it annihilates about 4 million tons of matter, transforming it directly into the energy that radiates outward and ultimately sustains all life on Earth. The journey of this energy from the core to the surface is an epic in itself. A single photon of light born in the fusion furnace of the core does not travel in a straight line. It embarks on what is known as a random walk, being absorbed by a particle of plasma and then re-emitted in a random direction, only to be absorbed again moments later. This process repeats countless trillions of times, causing the photon's path to be an impossibly convoluted and tortuous one. The plasma in the radiative zone is so dense that the photon's progress is painstakingly slow. It is estimated that it can take, on average, anywhere from 100,000 to over 170,000 years for the energy created in a single fusion event to finally reach the photosphere and escape into space. In a very real sense, the sunlight that warmed your face today was generated deep within the sun's core long before the dawn of human civilization. Once that energy is finally liberated from the photosphere, it crosses the vast expanse of space at the ultimate cosmic speed limit. The light itself, a stream of photons, completes its 150 million kilometer, or 93 million mile, journey to our planet in just 8 minutes and 20 seconds. This means that if the sun were to suddenly and impossibly cease to shine, we would remain blissfully unaware for over 8 minutes, continuing to see it in our sky as it was in its immediate past. But the sun emits more than just light. It constantly exhales a tenuous, high-speed stream of charged particles, mostly electrons and protons, known as the solar wind. This wind flows outward from the superheated corona, accelerating as it leaves the sun and streaming through the solar system at speeds that can exceed 800 kilometers per second, or 500 miles per second. This perpetual outflow of solar material is the extension of the sun's atmosphere, and it fills the entire heliosphere, interacting with every planet and celestial body it encounters. When this solar wind reaches our world, it collides with the Earth's protective magnetic field, the magnetosphere. Most of the charged particles are deflected safely around our planet, but some become trapped, spiraling down along the magnetic field lines toward the polar regions. There, they slam into the atoms and molecules of our upper atmosphere, primarily oxygen and nitrogen, causing them to glow like a celestial neon sign. This beautiful, shimmering light show is the aurora borealis, or the northern lights, and its southern counterpart, the aurora australis. The vibrant colors of the aurora are a direct record of this cosmic collision. The common green and rarer red hues are created by excited oxygen atoms, while the blues and purples are generated by nitrogen. The sunlight that reaches us is a rich tapestry woven from threads of different energies. It spans the entire electromagnetic spectrum, a continuous broadcast of information and power. While our eyes are tuned to see only the narrow band of visible light, the sun also bathes our planet in other forms of radiation. There are the long, gentle wavelengths of infrared radiation, which we feel as warmth on our skin. There are the radio waves, the same kind we use for communication. And then there are the high energy, shorter wavelengths, the X-rays and gamma rays, and most significantly for life on Earth, the ultraviolet light. This ultraviolet, or UV radiation, carries enough energy to be damaging to living tissue, causing sunburn and, with prolonged exposure, more serious harm. Fortunately, our planet has evolved its own celestial shield. High in the stratosphere, a delicate layer of ozone, a molecule made of 3 oxygen atoms, diligently absorbs the vast majority of the sun's most harmful high-energy ultraviolet radiation. This unassuming atmospheric layer is the silent, unsung guardian of life on the surface, making our world a safe harbor in the cosmic radiation storm. Yet, even the filtered UV light that does reach the surface possesses a remarkable quality. The sun's UV rays have potent antiseptic properties, capable of sterilizing surfaces and purifying water. A natural disinfectant that has been implicitly understood by cultures for millennia. It is a reminder that the sun's energy is a force of both creation and purification, a constant, life-giving presence in our sky. While the sun's daily output of energy is the very bedrock of our existence, its moments of violent, unpredictable rage serve as a stark reminder of its untamed power. The most potent of these outbursts are solar flares, which erupt from the magnetically chaotic regions around sunspots. These are not mere flashes of light. They are cataclysmic events that unleash the full fury of the star's magnetic engine. The energy released in a large solar flare is almost beyond human comprehension, capable of dwarfing the power of millions of 100 megatons hydrogen bombs detonating simultaneously. This torrent of energy, primarily in the form of X-rays and ultraviolet radiation, travels at the speed of light, reaching Earth in just over 8 minutes. A major flare can instantly disrupt radio communications on the sunlit side of our planet and poses a significant radiation hazard to astronauts in orbit. Closely associated with these flares are even grander events known as solar radiation storms. These occur when the same magnetic explosion that triggers a flare also acts like a colossal particle accelerator, grabbing vast quantities of protons and other charged particles from the corona and flinging them out into space at nearly the speed of light. These relativistic particles can arrive at Earth in a matter of minutes, long before the slower-moving plasma of a coronal mass ejection. A severe solar radiation storm can saturate satellite electronics, causing them to malfunction or fail, and can deliver dangerous doses of radiation to passengers and crew on high-altitude polar flights, sometimes forcing airlines to reroute air traffic to safer, lower latitudes. The most formidable of all solar eruptions, however, is the coronal mass ejection, or CME. While often linked to flares, a CME is a distinct and arguably more impactful phenomenon. It is the physical expulsion of a gargantuan bubble of plasma and embedded magnetic field from the sun's corona. Billions of tons of solar material are heaved into space, traveling at speeds that can range from a leisurely few hundred to a violent several thousand kilometers per second. If a CME is aimed at Earth, it can take anywhere from 1 to 4 days to cross the interplanetary void. When it arrives, this magnetized cloud of plasma slams into Earth's magnetosphere, compressing it and triggering a global disturbance known as a geomagnetic storm. It is these storms that can overload power grids, disrupt satellite navigation systems, and create the most spectacular auroral displays, sometimes visible in latitudes as far south as the Caribbean. As we contemplate this cycle of solar activity, we are inevitably led to consider the sun's own life story, its past, present, and future. Our star is currently in its comfortable middle age, a stable and predictable main sequence star. It is approximately 4.6 billion years old, a figure derived from the radioactive dating of the oldest meteorites, which are pristine, leftover building blocks from the formation of the solar system. The Sun is roughly halfway through its long and placid life, a 10 billion year span during which it will calmly fuse hydrogen into helium in its core. For now, it is a beacon of stability, providing the steady, reliable energy that has allowed life on Earth to evolve and thrive over billions of years. But this tranquil state cannot last forever. The Sun's life is governed by the finite supply of hydrogen fuel in its core. It is predicted to continue burning hydrogen as it does now for another 5 billion years. During this immense future span, it will gradually grow brighter and hotter, a slow, inexorable warming that will one day have profound consequences for our planet. But the true drama begins when the hydrogen in the core is finally exhausted. When this critical moment arrives, the nuclear fusion of hydrogen will cease, and the delicate balance between the inward crush of gravity and the outward push of fusion energy will be broken. Gravity will win the initial battle, causing the core to contract and heat up immensely. This heating will ignite a shell of hydrogen burning around the now inert helium core, and this new, ferocious energy source will cause the Sun's outer layers to expand dramatically. Our star will begin its transformation into a red giant. This swelling will be of an almost unimaginable scale. The Sun will grow so large that it will first consume the innermost planet, Mercury, and then Venus. Its expanding, tenuous atmosphere will likely reach the orbit of Earth, engulfing our world in the fiery tendrils of the dying star. It is a fate that lies so far in the future as to be abstract, but it is the scientifically supported destiny of our home. This red giant phase, a period of stellar gigantism, will last for about 1 billion years. The Sun will be a bloated, luminous, and relatively cool star, its ruddy glow filling the sky of any surviving outer planets. After this phase, the Sun's final act begins. The helium core, having contracted and heated for 1 billion years, will finally become hot and dense enough to ignite helium fusion, a process that creates carbon. This will provide a temporary reprieve, but the Sun's fate is sealed. It is not massive enough to fuse heavier elements, and so, once the helium is spent, the nuclear fires will die out for good. With its energy source extinguished, gravity will claim its final victory. The Sun's outer layers will drift away into space, creating a beautiful, glowing shell of gas known as a planetary nebula. At the center of this expanding cosmic smoke ring will be the Sun's last remnant, a white dwarf. This will be the collapsed, super-dense core of the former star, an object about the size of the Earth, but containing roughly half of the Sun's original mass. It will be a stellar cinder, no longer generating new heat, that will simply cool and fade over trillions of years, a diamond in the eternal night. Even the celestial mechanics of our local system will change over these vast timescales. In a more immediate, though still distant, future, the very spectacle of a total solar eclipse will become a thing of the past. The moon is currently, and very slowly, drifting away from the Earth. In about 600 million years, it will have moved far enough away that its apparent size in our sky will be too small to completely cover the disk of the sun. Total solar eclipses, that brief and breathtaking alignment of cosmic bodies, will cease to occur. Finally, our sun's place in the grand cosmic genealogy is as a population 1 star. This is not a ranking of importance, but a classification of its chemical composition and age. Population 1 stars, like our sun, are relatively young and are rich in metals. Those elements heavier than hydrogen and helium. This indicates that they were formed from interstellar clouds that had been seeded by previous generations of stars, the more ancient and metal-poor population 2 stars. The very existence of rocky planets like Earth and of life itself is only possible because our star belongs to this second, enriched generation. Humanity's quest to understand the sun is a story as old as thought itself, a narrative that begins not with telescopes and spacecraft, but with the first glimmer of philosophical inquiry. For millennia, the sun was a deity, a divine chariot, a perfect and unchanging celestial fire. It was the ancient Greek philosopher Anaxagoras of Clazomenae, who, around 450 years before the Common Era, made a revolutionary and dangerous leap of intellect. He was perhaps the first person in recorded history to dare suggest that the sun was not a god, but rather a physical object, a gigantic, incandescent rock, far larger than the whole of Greece. This idea that the sun was a star, just like the countless pinpricks of light that filled the night sky, was a profound departure from mythological belief and a foundational step toward a scientific cosmology. For this and other perceived impieties, Anaxagoras was exiled from Athens, a stark reminder that challenging the established order of the cosmos has always carried a heavy price. Our ancestors' careful observations of the heavens also led to the recording of its most dramatic events. The earliest known record of a total solar eclipse that can be confidently identified was not etched into paper or parchment, but inscribed onto a clay tablet in the ancient Syrian city of Ugarit. Archaeologists and historians, by cross-referencing the text with astronomical software, have dated this celestial event to March 5th, 123 years before the Common Era. The tablet describes the sky darkening in the middle of the day, a moment of profound and terrifying awe for the people of Ugarit, and a precious, unambiguous data point for modern science. The The technological means to capture the sun's image, however, would not arrive for more than 3,000 years. In the mid-19th century, the burgeoning art and science of photography was taking its first tentative steps. In 1845, two French physicists, Louis Fizeau and Léon Foucault, who were collaborators and later bitter rivals in the quest to measure the speed of light, pointed a camera at the sun and created the first ever detailed photograph of its surface. They used the daguerreotype process, an early photographic technique that produced a single, highly detailed image on a polished silver plate. Their groundbreaking photograph, a mere 5 inches in diameter, revealed the phenomenon of limb darkening, the observation that the sun's disk appears darker at its edges than at its center, and clearly showed a large sunspot group. For the first time, the sun was not just an object to be drawn or described, but one that could be captured and studied with objective, repeatable precision. This tradition of capturing our star in ever greater detail continues to this day, reaching its current zenith with instruments like the Daniel K. Inouye Solar Telescope. Perched high atop the Haleakala volcano in Hawaii, this modern marvel boasts a primary mirror 4 meters, or over 13 feet, in diameter, making it the largest solar telescope on Earth. It has produced the highest resolution images of the sun's surface ever taken, revealing features as small as a few dozen kilometers across. These astonishing images show the photosphere not as a smooth, uniform surface, but as a seething, granular patchwork of convection cells, each one a boiling plume of plasma about the size of the state of Texas. It is a view of the sun that is as turbulent and alive as it is beautiful. To truly understand the sun, however, we had to leave the surface of the Earth and journey into space. The space age brought with it the dawn of heliophysics. The first spacecraft to break free from Earth's orbit and enter a path around the sun was a small, unassuming probe called Pioneer 5. Launched in 1960, this 100-pound or 43-kilogram sphere was a marvel of early space engineering. It traveled between the orbits of Earth and Venus, providing the first ever in situ measurements of the interplanetary magnetic field and the solar wind, confirming the existence of the very phenomena that theorists had predicted. It was our first robotic emissary to the sun. The ultimate journey, however, would be to touch the sun itself. In a mission that sounds like something from mythology, the Parker Solar Probe, launched in 2018, became the first spacecraft in history to fly through the sun's upper atmosphere. In 2021, it officially crossed into the corona, sampling the particles and magnetic fields of this mysterious, superheated region directly. Enduring temperatures that would vaporize any ordinary craft, protected by a revolutionary carbon composite heat shield, the probe has swooped closer to the sun than any object ever built by human hands, sending back data that is fundamentally reshaping our understanding of the corona and the solar wind. Sustaining our long-term watch on the sun has been the task of dedicated solar observatories in space. Chief among these is the Solar and Heliospheric Observatory, or SOHO, a joint mission between NASA and the European Space Agency. Launched in 1995 and still operational today, SOHO has been our steadfast eye on the sun for over a quarter of a century. Positioned at a stable gravitational point between the Earth and the sun, it has provided an uninterrupted stream of data and imagery, revolutionizing solar forecasting and becoming the most prolific discoverer of comets in history, spotting thousands of them as they make their final sun-grazing plunge. From our vantage point here on Earth, the sun's sheer brilliance dominates our sky and our senses. Its brightness is measured on a scale of apparent magnitude, where lower numbers indicate brighter objects. The sun clocks in at a dazzling minus 26.74, making it far and away the brightest object we can see, over 400,000 times brighter than the full moon. This overwhelming luminosity is a direct consequence of its proximity and its immense energy output. It is this brilliance that also carries an inherent danger. It is never, under any circumstances, safe to look directly at the sun with the naked eye or through unfiltered optics like binoculars or telescopes. The intense visible light can cause permanent retinal damage, while the invisible infrared radiation can literally cook the eye's tissues, leading to blindness. Proper, certified solar filters are an absolute necessity for safe observation. The sun's name in our own language is a simple Anglo-Saxon word, but its alternate name, Sol, carries a deeper historical resonance. Sol is the Latin word for sun, and it was the name of the Roman god of the sun, the counterpart to the Greek god Helios. It is from this Latin root that we derive words like solar, solstice, and even parasol, an echo of an ancient culture's reverence for the star that ruled its days. This nomenclature extends to our entire celestial neighborhood. The term solar system is not just a convenient label. It is a literal description, meaning, quite simply, the system of the sun. It is a humble and accurate acknowledgement that everything in our cosmic family, planets, moons, and all the rest, owes its allegiance and its very existence to this one central star. The very light that reveals the sun's secrets also carries the story of its composition, a story that led to one of the most elegant discoveries in the history of science. It concerns the element helium, which derives its name from the Greek god of the sun, Helios, for a very specific and beautiful reason. During the total solar eclipse of 1868, the French astronomer Jules Janssen trained a new instrument, the spectroscope, on the solar chromosphere, that thin, reddish layer of the sun's atmosphere. The device split the sun's light into its constituent colors, a rainbow spectrum riddled with dark and bright lines, each one a unique fingerprint of a specific chemical element. Janssen noticed a brilliant yellow line in the spectrum that he could not account for. It did not match the signature of sodium or hydrogen or any other element known to exist on Earth. He had found the spectral ghost of an element that, as far as anyone knew, existed only in the Sun. For over a quarter of a century, helium remained a celestial curiosity, an element without a home on our own world, until it was finally isolated in a laboratory on Earth. It was a stunning confirmation that the same chemical laws that govern our planet also govern the stars, and a testament to the power of light to carry information across the vastness of space. Beyond its light and chemical makeup, the Sun's most profound influence is exerted in utter saya, through the invisible, inescapable force of its gravity. It is the Sun's immense mass that warps the fabric of space-time around it, creating a deep gravitational well that holds every planet, moon, and speck of dust in its thrall. The planets are not so much circling the Sun as they are perpetually falling toward it, but their immense sideways momentum, a legacy of the rotating nebula from which they formed, means they constantly miss. This perfect balance between forward motion and the inward pull of gravity is what we call an orbit, a stable, repeating path that has allowed the Earth to enjoy a relatively constant climate for billions of years. The Sun's gravity is the silent choreographer of our solar system's grand ballet. To quantify this force, we can imagine an impossible scenario: standing upon the Sun's visible surface. Here, the gravitational pull is about 28 times stronger than the gravity on Earth. A person who weighs 80 kilograms on Earth, or roughly 175 pounds, would be crushed under an effective weight of over 1,200 kilograms, or nearly 5,000 pounds. This immense gravity is the force that contains the Sun's own explosive nuclear fusion, maintaining the delicate equilibrium that defines its long and stable life. Yet, this stability is punctuated by a slow, rhythmic pulse of activity. The Sun's behavior, particularly the number of sunspots on its surface and the frequency of solar flares, follows an approximately 11-year cycle. This is the solar cycle, a gradual waxing and waning of magnetic activity driven by the star's complex internal dynamo. At the beginning of a cycle, known as solar minimum, the Sun can be placid and nearly spotless for weeks at a time. As the cycle progresses, sunspots begin to appear at the mid-latitudes and slowly migrate toward the equator, and the frequency of flares and coronal mass ejections increases dramatically, peaking at solar maximum. Then, just as gradually, the activity subsides, returning to a quiet minimum before a new cycle, with a reversed magnetic polarity, begins. This cycle is not merely an academic curiosity. Its consequences are felt directly here on Earth. An increase in solar activity, particularly during solar maximum, can have a profound impact on our technologically dependent civilization. A powerful coronal mass ejection can trigger a geomagnetic storm that disrupts our communications, damages sensitive satellite electronics, and can even induce powerful electrical currents in long conductors on the ground. These geomagnetically induced currents can overload transformers and trip circuit breakers, potentially leading to widespread and long-lasting power grid failures. The sun's temperamental moods are a constant and serious consideration for the engineers who manage our modern world. Humanity's relationship with the sun's rhythms, however, is far more ancient than our power grids. Our very concept of the year is defined by the Earth's 365-day journey around the sun. Our modern calendar is a direct inheritance of this solar reality. A sophisticated tool for tracking the seasons that was born from the agricultural necessity of knowing when to plant and when to harvest. It is a system of timekeeping that replaced earlier, less precise lunar calendars, cementing the sun's role as the ultimate arbiter of our lives. For all of its local dominance, however, our sun is humbled when placed in a broader cosmic context. In the vast stellar zoo of the Milky Way, there are stars that beggar the imagination. Consider the red hypergiant UY Scuti, one of the largest known stars by volume. It is estimated to be about 1,700 times wider than our sun. If you were to place this behemoth at the center of our solar system, its visible surface would extend far beyond the orbit of Jupiter. The Earth and all the inner planets would be vaporized deep within its tenuous, cool atmosphere. This comparison serves as a powerful reminder that our bright, powerful sun is, on a galactic scale, a relatively modest star. Yet it commands its own vast domain, a bubble of influence carved out of interstellar space called the heliosphere. This is the true extent of the solar system, a region inflated by the constant outward pressure of the solar wind, which pushes back against the gas and dust of the galaxy. This magnetic cocoon shields the planets from the majority of high-energy galactic cosmic rays, making the solar system a relatively safe harbor for life. To understand the sun's deep interior, from which all of this activity originates, scientists have developed a remarkable field of study known as helioseismology. Just as geologists study seismic waves from earthquakes to map the interior of the Earth, helioseismologists study the subtle, rhythmic oscillations on the sun's surface. The entire sun vibrates with millions of different acoustic wave patterns, causing its surface to gently pulse in and out. By carefully tracking these 2-minute oscillations, scientists can infer the temperature, density, and rotation rate of the sun's unseen depths with astonishing precision. It is through this solar sonogram that we have mapped the core, the radiative zone, and the convection zone. Finally, recent discoveries have revealed a more delicate and complex structure within our solar system. A series of faint dust rings that circle the sun, tracing the orbits of the planets. These are not solid, bright rings like Saturn's, but rather diffuse bands of interplanetary dust, some of it shed by comets and some from asteroid collisions. A particularly notable ring has been found to be associated with the orbit of Venus, with the planet's gravity shepherding the dust into a distinct, ghostly circle. These discoveries paint a picture of a solar system that is not empty space, but is filled with a fine, intricate web of material, all of it illuminated by and orbiting our central star. When the sun's volatile outbursts reach our world, they can trigger a planetary scale event known as a geomagnetic storm. This is not a storm in the meteorological sense, with wind and rain, but a profound and global disturbance of Earth's magnetic field. It begins when a coronal mass ejection, that billion-ton cloud of magnetized plasma, slams into our planet's protective magnetosphere. The impact is akin to a physical blow, compressing the magnetic field on the day side of the Earth and stretching it into a long, distorted tail on the night side. This sudden reconfiguration of our planet's magnetic architecture induces massive electrical currents in the upper atmosphere and can cause the radiation belts that encircle our world to become energized and unstable. The consequences of such a storm can be both beautiful and hazardous, leading to brilliant auroral displays at low latitudes, but also posing a significant threat to our technological infrastructure. The raw power that fuels these storms originates in the intricate magnetic ballet of the sun's atmosphere, and it is here we find the solar flare, an even more concentrated and sudden release of energy. A flare is born from the process of magnetic reconnection, where the intensely tangled magnetic field lines above a sunspot group suddenly snap and realign into a simpler, lower energy configuration. This process is astonishingly efficient at converting stored magnetic energy into other forms, including heat, light, and the kinetic energy of accelerated particles. The sheer amount of energy unleashed in even a modest solar flare is difficult to put into perspective. It can be more than 10 million times greater than the energy released by a large volcanic eruption on Earth. An event that can reshape the surface of our own planet is utterly dwarfed by a routine flash of anger from our star. To understand how we know so much about these distant, violent events, we must look not just at the light the sun emits, but at the light it absorbs. When we pass sunlight through a prism, we do not see a perfect, unbroken rainbow. The solar spectrum is actually cross-hatched by thousands of fine, dark lines. These features, first mapped in detail by the German physicist Joseph von Fraunhofer in the early 19th century, are absorption lines. Each dark line corresponds to a specific wavelength of light that has been absorbed by a particular chemical element in the cooler, upper layers of the sun's atmosphere. Like a cosmic barcode, these Fraunhofer lines provide a precise and unambiguous census of the sun's elemental composition, allowing us to know what our star is made of from a distance of 150 million kilometers, or 93 million miles. This deep, scientific understanding of the sun is a relatively modern achievement. For most of human history, our star was a subject of mythology and reverence, a powerful deity who commanded the sky and brought life to the world. In the sophisticated pantheon of ancient Egypt, this deity was Ra, the falcon-headed god who was believed to sail across the sky each day in a celestial barge. Ra was the king of the gods, the creator of all things, and his daily journey was a symbol of the eternal cycle of birth, death, and rebirth. Temples were aligned to the rising sun, and the pharaohs themselves were considered to be the sons of Ra, their divine right to rule flowing directly from the solar deity. A similar reverence was found in ancient Greece, where the sun god was Helios, a handsome titan who drove a golden chariot drawn by 4 fiery horses across the heavens each day. It was Helios who saw and heard everything that happened on Earth, an all-knowing observer whose daily journey was a testament to cosmic order and regularity. His sister was Selene, the goddess of the moon, and his brother was Eos, the god of the dawn, a celestial family that governed the rhythms of day and night. The Norse people of ancient Scandinavia had their own unique and compelling solar mythology. For them, the sun was a goddess named Sol, who, like Helios, drove a chariot across the sky, relentlessly pursued by a great wolf named Skjold. According to the prophecy of Ragnarok, the Norse apocalypse, Skjold would one day catch and devour Sol, plunging the world into a final, deep winter. This mythological narrative of a constant, desperate chase across the heavens reflects the harsh realities of life at high northern latitudes, where the return of the sun after a long, dark winter was a matter of life and death. Our modern explorations of the cosmos have revealed that our own solar system, with its single central star, is not the only possible arrangement. We have discovered a fascinating variety of exoplanets that orbit multiple stars' worlds where the concept of a single sunrise would be entirely alien. A striking example is the system known as Kepler-64, which hosts a planet, Kepler-64b, that is part of a 4-star system. The planet orbits a close pair of stars, which are in turn orbited by a second, more distant pair of stars. A being on this world would experience a complex and ever-changing cycle of light and shadow, with multiple suns of different brightness and color tracing intricate paths across its sky. These discoveries have expanded our understanding of how planetary systems can form and have shown that the universe is even more creative and diverse than we had ever imagined. And just as some systems have more than one star, some stars are of a size that makes our own sun seem utterly insignificant. In the constellation Scutum lies Stephenson 218, a red hypergiant star that is currently one of the leading candidates for the largest known star by physical size. With an estimated radius about 2,150 times that of our Sun, its sheer scale is mind-boggling. If it were to replace our Sun, its surface would engulf the orbit of Saturn. This star is so large and so luminous that it shines with the light of nearly 500,000 suns. It is a true celestial monster, a star living out its final, bloated stages of life before it collapses and explodes in a spectacular supernova. Yet, for us, here on Earth, our sun's brilliance is all that matters. After the sun itself, the next brightest star in our sky is Sirius, often called the Dog Star, located in the constellation Canis Major. While Sirius is an intrinsically much brighter and more massive star than our Sun, it lies at a vastly greater distance, over 8.5 light years away. Its apparent brightness in our sky, while impressive, is a mere flicker compared to the overwhelming, life-sustaining glare of our own star. This illustrates the profound importance of proximity in our perception of the cosmos. The Sun appears as the largest and brightest object, not because it is the most powerful star in the galaxy, but simply because it is ours. The apparent and coincidental similarity in size between the Sun and Moon in our sky is a fortunate astronomical accident, a geometric conspiracy that has granted humanity one of nature's most spectacular sights, the total solar eclipse. This beautiful illusion is born from a simple but profound ratio. The Sun is approximately 391 times farther away from the Earth than the Moon is. By a remarkable cosmic coincidence, the Sun's diameter is also about 400 times larger than the Moon's. These two ratios nearly cancel each other out, resulting in both objects appearing to be almost exactly the same size in our sky. This happy accident allows the small, nearby Moon to perfectly obscure the enormous, distant Sun, creating the brief and breathtaking moments of totality. However, this celestial alignment is not static. Our planet's orbit around the Sun is not a perfect circle, but a gentle ellipse, a fact first mathematically described by the German astronomer Johannes Kepler in the early 17th century. This means that the distance between the Earth and the Sun changes throughout the year. We are closest to the Sun in early January, a point in our orbit known as perihelion, and farthest away in early July, at a point called aphelion. The difference is only about 5 million kilometers, or 3 million miles, and it has a very minor effect on our seasons, which are primarily caused by the tilt of the Earth's axis. However, this changing distance does cause the Sun's apparent size in our sky to vary slightly, a subtle but measurable factor that influences the duration and type of solar eclipses. If the sun's gravitational anchor were to suddenly vanish, the consequences for our planet would be instantaneous and absolute. In that impossible moment, the Earth would cease to follow its curved orbital path and would instead fly off in a straight line into the void, a silent, dark wanderer continuing on a trajectory tangent to its former orbit. It would become a rogue planet, its momentum carrying it out of the solar system and into the vast, cold emptiness of interstellar space. The complex, dynamic behavior we observe on the sun's surface, the sunspots, the flares, the prominences, is all driven by a force that originates deep within its interior. The sun's churning, convective motions, combined with its differential rotation, create a powerful and complex system of electrical currents. Just as a current flowing through a wire on Earth generates a magnetic field, these colossal currents of flowing plasma inside the sun generate its immense and ever-changing magnetic field. This process, known as a stellar dynamo, is the engine that powers the entire cycle of solar activity, transforming the kinetic energy of the sun's rotation into magnetic energy, which is then released in the dramatic outbursts we observe from afar. The particles ejected during these outbursts pose a real and present danger that extends beyond our technological systems. Passengers and crew members in high-flying, long-haul aircraft, particularly those on routes that cross over the Earth's polar regions, can be exposed to significantly higher levels of solar radiation during an extreme solar storm. The Earth's atmosphere provides a substantial shield against cosmic radiation, but at cruising altitudes of 10 to 12 kilometers, or roughly 33,000 to 39,000 feet, that protection is diminished. During a powerful solar particle event, radiation levels can spike, delivering a dose in a single flight that can be equivalent to multiple medical X-rays. For this reason, aviation authorities and airlines closely monitor solar weather forecasts, sometimes rerouting flights to lower altitudes or more southerly latitudes to ensure the safety of everyone on board. We track these solar moods using a numbering system for the solar cycles, a continuous record that allows scientists to study long-term patterns in the sun's behavior. We are currently living in solar cycle 25, which officially began in December of 2019, when solar activity reached its last minimum. Each cycle is like a heartbeat of the sun, a rhythmic pulse that takes roughly 11 years to complete. Scientists are now carefully watching as this new cycle ramps up toward its predicted peak. The forecast for the current cycle, based on a combination of computer models and historical data, suggests that the maximum level of solar activity will likely occur around July of 2025. This period of solar maximum is expected to bring a significant increase in the frequency and intensity of solar flares and coronal mass ejections, promising more spectacular auroral displays but also posing a greater risk of disruption to our satellites, power grids, and communication systems. The potential for such disruption is not merely theoretical. We have seen it happen before. In December of 2006, during the declining phase of solar cycle, 23, a particularly intense X-class solar flare erupted from a sunspot region on the Sun's eastern limb. The blast of X-rays was so powerful that it overwhelmed the sensors on the GOES satellite that monitors the Sun, and it had an immediate and direct impact on technology we use every day. The flare's radiation ionized the Earth's upper atmosphere, causing significant disruptions to the Global Positioning System, or GPS. For about 10 minutes, high-precision GPS signals used for surveying, drilling, and other sensitive applications were rendered unreliable or completely unavailable, a clear demonstration of our vulnerability to the Sun's sudden whims. The light the Sun sends our way is a multifaceted gift, containing a spectrum of energies that have profoundly different effects on our world. While our eyes perceive the visible portion of the spectrum, the Sun does not only emit visible light, it also broadcasts a continuous stream of other forms of electromagnetic radiation, from the low-energy radio waves to the incredibly high-energy gamma rays produced in nuclear reactions. This full spectrum of radiation is the primary driver of Earth's climate and weather systems, providing the energy that heats the land, evaporates water from the oceans, and drives the atmospheric circulation patterns that create winds and storms. It is the engine of our planet. This solar energy is the fundamental power source for almost all life on Earth, captured and converted through the elegant biochemical process of photosynthesis. This is the miracle of turning sunlight into life. Plants, algae, and some bacteria use the sun's energy to convert carbon dioxide and water into glucose, a simple sugar that provides the chemical energy for their growth and metabolism. This process not only forms the base of nearly every food chain on the planet, but also, as a crucial byproduct, releases the oxygen that we and most other animals need to breathe. In a very real sense, every bite of food we eat and every breath we take is a gift from the sun, a tangible link to the nuclear furnace burning 93 million miles away. The sun's constant activity and the ceaseless outward flow of the solar wind come at a cost to the star itself. Every second, the sun sheds a colossal amount of its own substance, casting it off into the interplanetary medium. Through the solar wind, it loses approximately 1.5 million tons of matter every single second. When combined with the 4 million tons of mass converted directly into energy via nuclear fusion in its core, the sun's total mass loss is a staggering 5.5 million tons per second. While this number sounds immense on a human scale, it is almost insignificant when compared to the sun's total mass. Over the course of its entire 4.6 billion year life, the sun has lost only about 1/100% of its total mass, a testament to its sheer scale and the vast reserves of fuel it still holds. This colossal, life-giving body is, and will remain for the foreseeable future, the closest star to Earth. This simple fact is the single most important aspect of our planet's existence. While the night sky is filled with countless other suns, some larger and brighter than our own, their immense distances render them little more than beautiful, cold points of light. The next nearest star, Proxima Centauri, is over 4.2 light-years away, nearly 300,000 times farther from us than the Sun. It is our star's proximity that provides the warmth, light, and energy necessary for life to have taken hold and flourished on our world. Our star reigns alone in the center of our solar system, a solitary monarch commanding its planetary court. Unlike many other star systems we have discovered, which feature 2 or more stars in complex orbital dances, our Sun does not have any stellar companions. It also does not have any moons of its own. Moons are natural satellites that orbit planets, dwarf planets, or even large asteroids, but not stars themselves. The Sun's immense gravity and the turbulent, high-temperature environment in its immediate vicinity make it impossible for any smaller body to maintain a stable orbit close enough to be considered a moon. The planets, held in their distant, stable orbits, are the Sun's only true companions. The Sun's magnetic field, the engine of all its dramatic activity, is a force of incredible complexity and strength. On average, the Sun's global magnetic field is only about twice as strong as the Earth's surface field. However, this average value is deeply misleading. In the dark, cool hearts of sunspots, the magnetic field becomes incredibly concentrated, twisted into tight bundles by the Sun's churning motion. In these localized regions, the magnetic field can be thousands of times stronger than the Earth's, reaching strengths that are difficult to replicate in laboratories on our planet. It is this intense, concentrated magnetism that inhibits the flow of heat and gives birth to all the spectacular phenomena of the active Sun. The Sun's surface is a canvas of constant, frenetic activity, painted with features that are often too small or too fleeting to be seen with anything but our most powerful solar telescopes. At any given moment, the chromosphere, that turbulent layer just above the visible surface, is populated by a veritable forest of as many as 10 million small, jet-like eruptions called spicules. These fiery tendrils of plasma, typically a few hundred kilometers across and several thousand kilometers long, are constantly shooting upward from the lower atmosphere at high speeds, lasting for only a few minutes before they collapse and fade. They are thought to play a crucial role in transferring mass and energy from the Sun's lower atmosphere into the superheated corona, acting as a kind of convective elevator for solar material. While the Sun's outer layers are a tenuous, superheated gas, its deep interior, is a place of almost unimaginable density. The pressure at the Sun's core is over 260 billion times the atmospheric pressure at sea level on Earth. This immense pressure squeezes the core plasma to a density that is about 150 times the density of water. A single tablespoon of material from the Sun's core would weigh over 1.5 kilograms, or more than 3 pounds, on Earth. It is this extreme density, combined with the extreme temperatures, that creates the perfect conditions for the nuclear fusion reactions that power the star. In our modern scientific view, the Sun appears as a brilliant, yellowish white star. However, the Sun is actually white. It emits light across all wavelengths of the visible spectrum with roughly equal intensity. The reason it appears yellow to us is entirely a trick of our planet's atmosphere. The molecules in Earth's air are more effective at scattering shorter wavelength light, like blue and violet, than they are at scattering longer wavelength light, like red and yellow. This phenomenon, known as Rayleigh scattering, is the same reason our sky is blue. We are seeing the scattered blue light from all directions. When we look at the Sun, especially when it is lower in the sky, more of the blue light has been scattered away from our line of sight, leaving the remaining direct sunlight to appear more yellow or even red. From the vantage point of space, with no atmospheric filter, the Sun would be revealed in its true, brilliant white color. Just as the Earth is tilted on its axis, giving us our seasons, the Sun is also tilted. Its axis of rotation is tipped by about 7.25 degrees relative to the ecliptic plane, the plane of the Earth's orbit. This means that from our perspective, the Sun's north and south poles are not perfectly aligned with the north and south of our solar system. This tilt has a subtle but important influence on the heliosphere and the way the solar wind propagates out into space. The history of observing the Sun is punctuated by moments when its power has been made terrifyingly clear. In 1859, the English astronomer Richard Carrington was sketching a large sunspot group when he witnessed a blindingly bright flash of light, a white light flare. This was the Carrington event, the most intense geomagnetic storm in recorded history. The coronal mass ejection associated with the flare reached Earth in just over 17 hours, an incredibly fast journey. The resulting geomagnetic storm was so powerful that it caused telegraph systems across North America and Europe to fail, in some cases giving telegraph operators electric shocks and setting their paper reports on fire. The aurora were so bright that people in the Rocky Mountains reportedly woke up in the middle of the night, thinking it was dawn. A storm of this magnitude today would have a catastrophic impact on our modern, electrically dependent world. Finally, the Sun's light, particularly its ultraviolet radiation, plays an intimate and essential role in our own biology. When our skin is exposed to sunlight, it triggers a chemical reaction that synthesizes vitamin D, a crucial nutrient that is essential for absorbing calcium, maintaining strong bones, and supporting a healthy immune system. This direct physiological link between our bodies and the light of a distant star is a profound reminder of our deep connection to the cosmos. We are, in a very real sense, children of the sun. Our health and well-being tied directly to the light that it so generously provides. And so, our journey to the heart of the sun comes to a close, not with an end to the story, but with a new beginning in our understanding. The star we thought we knew has been transformed from a simple benevolent disk in the sky into the complex and living entity it truly is, a celestial engine of unimaginable power, a magnetic behemoth of stunning complexity, and the nuclear furnace that forged the conditions for our own consciousness. It is a star of profound dualities. The gentle warmth we feel on our skin is the product of the most violent process in our solar system, and the steady light that guides our days is governed by a cycle of magnetic chaos that can threaten our modern world. From the ancient myths that saw a god in its fire to the modern probes that taste its atmosphere, our quest to know the sun is a mirror for our own evolving intellect. The next time you step outside and feel its rays upon your face, perhaps you will remember their long journey, an odyssey of 100,000 years from the crushing pressures of the core to the silent expanse of space. You may see in the blue of the sky the scattered remnants of its true white light. You may feel in your own bones the legacy of the vitamin D it helps create. We have learned that we are connected to this star by more than just gravity and light. We are tied to it by chemistry, by history, and by the very rhythm of our lives. It is just one star among billions in our galaxy, a common yellow dwarf in a quiet suburban arm. But it is our star, for in its light, we not only see our world, we see ourselves, reflected in the fire of an ordinary star that has made our existence anything but.